All right. So happy Tuesday. And then, yeah, if we have questions about something, we could look at stuff. Otherwise, I did want to look at a quick overview of where we are in the quarter. So week 5, so we're going to do our last chapter before the exam. So colligative properties of solution. So we touched on molarity first quarter, but now we're going to go back and kind of do more solution practice. And with that, we're going to do the titration lab this week. That being said, so especially Tuesday people, you're gonna need some more advanced math that we don't know yet. So maybe hold off on the lab. My plan is Thursday that we'll have time, and then we'll go over the calculations we need for the titration lab. Because the math, like I said, is pretty involved for that one. And I may extend the due date for this one, so don't rush to turn it in, right? Like I said, we'll go over the math, and then you may need some time to work it out. And then that being said, okay, so then week 6, we're going to have our first exam, and it's going to be over everything we've covered, so 8 through 16. So we'll do our usual format, so we'll review on the Tuesday, have the exam on the Thursday. And then if you do have time accommodations, maybe, oh wait, there's going to be no lab, so sorry. I was going to say just think about that, because usually I'll just let you test normally, and then you can just run over time. And then there will be no lab, so this would be a good, though, lab makeup time on week 6. I think a few people have missed a lab or two, so week 6, let's plan for makeups, and so let me know what you missed so I can coordinate with the stock room. And what else is on the docket? Oh, I posted a link for this. So don't forget about REUs, NSF REUs, right, for research. The deadlines are variable, and some of them are coming up. I just checked out a few locally in Oregon. So this one is doing, some ocean research. But this one, blah, blah, blah. So February 15th, right? So that one's coming up pretty quickly. There's another one, robotics. That is, where's the deadline? I thought this one was also February. February 10th. So deadlines coming up for some NSF sites. So I posted the link so you can go search anywhere in the US for a site. And I'm more than happy, of course, to do a recommendation letter for y'all and help y'all. And of course, keep searching for scholarships independently. If you need help, I'm happy to sit down and work with y'all as well over that. Trying to think what else is on the docket. Oh, and then papers. So just kind of keeping that in mind. So I think I've commented on most people. I still have a few to grade. I've been a little behind on grading. So just kind of check the comments. Yeah, sorry. So yeah, next week the 12th is our exam. So yeah, look for comments on the paper. I think I like most people's topics. And then just, like I said, make sure you're getting help from me. All right, other things. So I did want to look at this problem to warm up. I know it's going back to kind of MO theory. But this one struck me as a good problem for a certain reason. Just because we have to kind of interpret what this is saying, and this gives us deeper implications. So maybe look at this for a second And notice it is a more advanced problem, but I think it's still value in kind of looking at this. And so we have the pi energy level diagram for trigonal planar species, such as nitrate ion is shown here. And of course, kind of the trick is sometimes chemists just give you this really abbreviated picture of our MO diagram. And so what's going on here, right? Use this pi energy diagram to describe our bonding in our nitrate ion. Kind of what is this from, right? What is the bond order in our nitrogen? So can we kind of rationalize where this diagram came from, including, right, who are these non-bonding ones? So maybe take a few minutes to try to draw out a structure and think about, huh? Yeah. So yeah, what are those non-bonding orbitals? So that's another good question as we kind of warm up. Yeah. Well, let's see. I mean, I feel like let's back up though. So where are these orbitals coming from, right? Because I don't necessarily want to fill in the electrons, right? They didn't show us, but I guess the bigger question is what orbitals are participating in bonding, and then which one are the non-bonding ones, and then how do we figure that out? You sure you don't want to guess? Or how could we approach this problem before we... Yeah, so draw out your Lewis dot structure, right? So that's kind of step one, if you haven't already. So what's the Lewis dot? And then as you're kind of drawing that in the back of your mind, you're starting to kind of think, what's the geometry? And of course, geometry is going to imply hybridization, right? And so, Skylar, I feel like maybe you'll come back to me with an answer. I feel like you do know the answer. You were looking at it back in this chapter. And then, yeah, chat came up with a kind of a thought, a double bond. But then I guess the question is, how many double bonds does it have in our Lewis dot structure? Oops. Well, that's we can discuss that in a second. So you guys are coming up with good questions. So is it 1? Is it 2? So then you're saying, okay, let's compare it to maybe 2. So the only thing I don't like about this having this structure is it's hypervalent for nitrogen, which we said typically nitrogen is not hypervalent. And again, the point isn't to be like, oh, this is wrong, right? The point is just kind of look at it, maybe reflect that this is not quite what this is showing either, right? Because there's several implications that this MO diagram is making that maybe you're not entirely clear, but that's something that we should be considering. And so yeah, like the chat was saying though, it does have to do with the number of double bonds. And so let's examine this structure for now. So we have our Lewis dot structure. Okay, so we have, right, our sigma bonds, which that's the other thing, right? They neglected our sigma bonds in our diagram. So you're probably right in that this is like the HOMO-LUMO gap. I'm not sure why they didn't explicitly fill in any electrons for us. And then they don't really show, right, any of the sigma bonding orbitals, right? So that's the other thing. So just kind of piecing it in your mind, well, you have your sigma down here, probably sigma antibonding way up here. But we're just kind of focusing on, again, our pi orbitals. Okay, so then where does our pi bonding orbital come from, right? And you can either look at your Lewis dot structure to tell you this, kind of look at this, right? What is giving rise to that pi bond? And if you don't know, go back to what I said about the hybridization. So what's the hybridization at oxygen and nitrogen and yeah, so what's yeah, so sp2, good. So I think we're starting to tease it out. So sp2, sp2. All right, so then what gives rise to our pi bonding orbitals? I mean, it does, but right, let's identify, so who's left? So the point is we're trying to figure out, well, who is left, right? So we said these are sp2 hybridized. So then how many p orbitals went into this sp2 hybridized system? Yeah, and then, so then the question is, so where is that extra p orbital? And what is that? Yep, and so right, so now we're saying, yes, this is where our pi bond is coming from, right? So now we're identifying on the chart. Okay, this is from this interaction. And I don't know if it's helpful for y'all to kind of write that. Okay, that's literally from my nitrogen oxygen double bond here. But then this has some interesting implications, which I'm not sure if you guys fully appreciate at this second in time. But let's see it, what it's thinking, what this is implying, and then what this also kind of means with our resonance structures. So what I'm getting at is, well, what's the hybridization on these oxygens? That's really a better way to phrase what I'm getting at. And what does that imply? What are the two possibilities? So how many things are attached to it potentially, right? Or 1, 2, 3 for this oxygen. Everything, right? So lone pairs, things attached. So there's 4 things. So then, right, it's kind of implying sp3 hybridization. So that's kind of one choice, right? But if we had something that was sp3 hybridized, then we wouldn't have pi non-bonding, right? Because they could never bond. So then, and I'll just kind of put this as, we'll call this option 1. And so this is my other point, right? Is again, like as a chemist, you're kind of evaluating what are the possibilities versus, again, how does this behave? And then, you know, again, like this could be from a computational program or something. And then you're like, well, what is this implying? And so what I'm getting at is, well, option 2, we'll call it, is, well, what if this is actually sp2 hybridized, right? Because Well, you guys might be aware that we can draw this double bond around, right, in a resonance structure. We kind of remember that, where we're just showing that the electron density is circling around, right, that we would have an average bond of 1 1/3 or so. And again, it's cycle around, so it doesn't matter what nitrogen is formally taking the double bond, because it should be delocalized, right? And so that's kind of the key then, is, well, in order for this to have any sort of delocalization, for this double bond to be able to shift to here, they have to have the same, like, hybridization and line up essentially. And so option 2 then is then it's really sp2 hybridized. So that means that these lone pairs, and maybe I'll go ahead and redraw this now. But that means that these oxygens, right, so then the lone pairs are actually, 2 of them are sp2 hybridized, and then that last one, your non-bonding one, is in that p, and let's just call it y for now, orbital. Yeah.
Are you just trying to say that they're all sp2, but then the free p kind of rotates between them, and one of them at one point is sp3?
Well, so probably we would say that these are never sp3. That's the implication of that, because that was the question. It's like, well, are they sp3? Are they not? Are they sp2? But then we find, in order for the bond to move around and have resonance, they have to be sp2. And so we'll kind of visit this idea later. I'm kind of just teasing it now because I saw that as a book problem, so now I'm just trying to redraw what we said. But so again, everything is sp2, and then we have, so these are our pi non-bonding formally, right? Because again, how we've taken this snapshot is we have our pi bond here. So again, we've just drawn it, right? So we've just drawn it. At this moment in time, the pi bond is here, but then for it to be delocalized across, these also have to be in, again, the correct geometry, right? So then we could move the double bond over here, make our new resonance structure, and we would have our pi bond. And then these would just formally shift, right? And so now this kind of makes more sense. And so now just, again, putting all the pieces together. So this was, again, our bonding NO in symmetry. And then, of course, we have to have our anti-bonding combination. And then, again, these are just our non-bonding on the other 2 oxygens. So that's just kind of cool, again, just to keep in mind, because this extra lone pair and where that is, right, that's super significant whether we can have pi bonding or not. And so this will come up again with nitrogen. And so this is a pesky issue with Chem that students generally fail to see this kind of either sp3 or sp2 with a y, with a py orbital. Trying to see that correctly in Chem is tricky. So that's why we're introducing it now. So again, when you see these, or you see maybe a nitrogen in a similar scenario, you're wondering, can it make a pi bond? And if it can make a pi bond, then it has to have that p orbital in the correct geometry orientation. Does that kind of make sense? All right, how are we feeling on other things, since we're kind of marching towards the midterm here? Sorry, I lost my mouse somehow. All right, so let's, oh.
So much of the chapter 15 homework was conceptual rather than math-based.
Yeah.
Test format is going to follow that as well. I mean, there's one, problem number 5.
Yeah, the tests will be a mix. So yeah, there'll probably be some conceptual questions. So there'll be a mix of multiple choice. And then expect the math to be like we did that heating diagram. So there'll definitely be math of that. And Yeah, PV equals nRT, but yeah, I'll base it off the homework. So a mix of questions. All right, so let's look at our colligative properties, which is in the winter time, so kind of appropriate, although it feels like spring is already here. And so we're given this scenario, so our frogs. So there's this special wood frog. And so unlike most cold-blooded animals, these wood frogs have the ability to survive cold temperatures by hibernating in a frozen state. And in this frozen state, the wood frog has no heartbeat, no blood circulation, no brain activity, and then it can be revived. And of course, what's the problem with freezing ice? It says it on the notes, but what do you guys know about, right? You try to like defrost your meat or your produce. What happens? Yeah, right. And so why is that? Yeah, I mean like ice, right? So it's like physically sharp, right? So it like literally slices all the yeah, so it slices all the cells, so right, your plants, your meat cells, so everything gets kind of destroyed, obviously. And so of course the wood frog conundrum is, well, we would expect there to be cell damage in our frog. And so the wood frog gets around this by flooding their blood with a large amount of sugar. And then that sugar prevents the blood from freezing then. And so we have freezing point depression there. And then kind of showing how that happens, so we can see how the glucose disrupts, right, our crystal packing structure of our water molecules, so then it has to go to a lower temperature to stop that motion. Yeah.
Even with preventing like ice, like wouldn't the cell still die from like lack of oxygen and everything else that it would still need, right?
I mean, I'm not sure how it survives because, I mean, it has to survive in some way, so it must just like suspend cellular activity, I assume, or something. Yeah. But yeah, I mean, our main focus was like, obviously, if it defrosts it, we can't have cellular damage, like physical. But yeah, I'm not sure like how it survives the lack of oxygen for such an extended period of time, or if it just like somehow shuts down everything.
It could just be the temperature massively slowing all of the reactions going on in the cells.
Yeah, but it's still pretty interesting. So I don't know like how quantified that is with like the reaction rate or like if there's any sort of diffusion at all. But yeah, that'd be pretty interesting to like deep dive research. And then, so like I said, we got a small taste of this last quarter. So refresher, so our solutions are homogeneous mixtures. And a mixture is two or more different chemical substances. And I think we've seen kind of different phases in the past. So solid liquid, gas and liquid, and gas and gas. So again, different mixtures. And so formally, we tend to define solutions as having a solute component. And so this is generally the minor component. I mean, again, not always. And then it's generally the solid component. Again, not always. And then our solvent is whatever medium our reaction takes place in. Just a good think back to first quarter when we did the baggy reaction and we kind of just watched the white powders stare at each other. That's kind of the point, right? Like we have to have some medium where everything can react in solution. And so for our purposes, we mainly see water or aqueous solutions. And like I've mentioned in organic chemistry, that would be any number of solvents, ether, toluene, DCM. Okay, we'll stop there. And so then blah, blah, blah. Solute is the component that is being dissolved into the solvent. And again, major is the solvent, minor is the solute. Just an aside, and I think somebody is interested in green chemistry. If you have a neat reaction, that means that you have no solvent. And so that's just kind of, the term that's popular now in green chemistry. So trying to have a liquid reagent. So that's like one way to have a neat reaction, right? So you have one liquid reagent, one solid reagent, and maybe if you heat it up, that'll be just good enough to have them react. And so like we've kind of looked at, so now I'm putting together our intermolecular forces chapter, right? So we have our saying like dissolves like. So looking at polar, mixing with polar molecules, and nonpolar, right, with nonpolar. So we can think of our examples. So right, polar with polar, thinking of ethanol and water. Again, they share hydrogen bonding or OH groups, so pretty similar. And again, so similar that they form an azeotrope. So really liking one another. And then nonpolar, I tend to think of like hexanes and oil, or thinking back right to the fat in the soap and how that long chain of our soap dissolved our grease. And then so nature has a tendency towards spontaneous mixing. So I think you guys are aware of that. I never bring the demo just because it seems too simple, like where you put the drop of water, or excuse me, drop of food coloring and water, and then it mixes out, yay. And or right, the same concept, spraying perfume in one corner, and then it'll diffuse and mix everywhere over time. And so that just tells us again that nature has a tendency towards spontaneity and mixing. So everything again will mix and spread homogeneously. Again, you can think about your molecules moving around, especially gas molecules. And mixing is also right energetically favorable, so it would take energy to try to split a mixture. And so we saw, like I said, we saw molarity in a very brief introduction to concentrations last quarter. So we're just kind of, again, refreshing it. And so like we mentioned, chemists deal with a variety of solutions and different concentrations and concentration units. So this is our kind of cheat sheet for this unit. So we have molarity, which again I believe we covered. So that's our most common chemistry unit. And so that's just defined as moles of our solute over solution. Then we have molality with an L there and a small lowercase m. So this I hardly see it used in practice. It's supposed to be used like by maybe analytical chemists or something, since it's technically more accurate. And so that is defined as the moles of your solute over the mass of your solvent in kilograms. So volume can vary slightly with temperature, so that's why molality is considered more accurate. And then, so I think we've seen mole fraction before, right? We saw it with our gases, but here it is again, just a reminder. So it's our moles of whatever we're interested in over the total moles. So of course, in this case, it's moles of solute over solvent. I'll just kind of put, right, total moles, like we've seen in mole fraction. And then we can convert that fraction to a percent. So we've seen that, just multiplying by 100. And then the rest of these kind of, I've given warnings, but yeah, it depends like how they're given. So you can have parts by mass, parts by volume, and just watch that, right? Is it a percentage? What is it given by? So often we've seen a percent by mass, and so those are pretty easy to calculate at least. And then we'll look at this in a little bit more detail, the parts per million, parts per billion. and our percentages. All right, so we remember molarity, or at least hopefully we do. So again, moles of solute per 1 liter of solution. And so just going through our example, if we have a sugar solution that contains 2 moles of sugar, then that means that 2 liters of that contains 4 liters, or excuse me, 4 moles of sugar. 0.5 liters is 1 mole of sugar. So again, I think we've looked at this. Then we've looked at, or we probably haven't looked at molality. So molality is again number of moles per kilogram, and it does not vary with temperature since it's based on masses. So like I said, more accurate. So watch for that little m. And then so parts per solute. So generally we measure in the same units. So like I said, always watch these. Is it grams, kilograms, volume? So it could be in any unit, right? So you just have to be cognizant. Or percentage, so right, parts per solute. So if it's 0.9% by mass, right, then you can always assume 100 grams. So then we have 0.9 grams of solute for 100 grams of solution. And then so parts per million, so that's defined as 1 part per a million parts. So 1 part over 1 times 10 to the 6. And so this can be kind of confusing in my opinion to convert between. And so I think the easiest way to look at these parts per million is treat it as milligrams of solute, so convert that to milligrams, over liters of solution, right? And so you can see how the units work out. So milligrams, 10 to the minus third, right, over kilograms, so 10 to the third. So that gives us our factor of 1 times 10 to the 6 there. So that's the best way to treat that. And like I said, we'll look at some examples. And then parts per billion, so same thing. So now we have 1 part per a billion, right? 1 times 10 to the 9th. And so it's convenient to look at this then as micrograms per kilogram. And so again, we can see where that factor comes in. So microgram 10 to the minus 6, kilogram 10 to the third, giving us, right, again, a 10 to the 9th factor of difference there. So in mole fraction, like I said, we've seen. So no units, just keep that in mind. All right, so let's try to practice now. So let's go ahead and do that. So we're preparing a solution. We have 17.2 grams of ethylene glycol and 0.5 kilograms of water. And our final volume is 515 milliliters. And so see if you can calculate the concentration in each of these units. So go ahead and take a few minutes. I'll let you guys try that out and then we'll check in. So let's kind of see how we're doing. So walk me through your molarity calculation. So what do we need to do for this one? So moles, so what's my molecular weight?
The AMU is 62.068.
And then, so how many moles did you get?
0.2771.
Excellent. Does that sound good? So then, okay, moles, and then what's molarity again?
It's mole divided by 1 liter of solution.
Or liters. And then, so then we got to convert this to liters. So then we can plug in for molarity. So 0.2771 then divided by 0.515. So then what do we get for our molarity?
I got 0.538.
0.538. And that looks good with the 3 sig figs. So lots of yeses in class. If you're in the chat, feel free to post your answers. All right, so that one was probably easy enough. And then, so let's try molality, right? So we can take our same amount and then find our grams. And then they told us the gram amount at least. They gave us both gram and volume, right? So they don't always do this in a problem either. So just keep in mind that otherwise for molality, you might have to think of some sort of density calculation, right? So it just kind of depends what information we're given, obviously. So like I said, in this case, they did happen to give us the kilogram amount. So now little m is moles over kilogram. I'll just steal this answer. So 0.2771 divided by 0.5. So what does that give you for your molality?
0.554.
So 0.554 little m. It looks like chat agrees. Everybody get that in here? Yeah, so these, like I said, hopefully these shouldn't be too difficult. On that note, so I will say this is probably like our last easier math. And then so after this, so again, we're going to take our tests. But then our math does get a little bit, I'll say it, slightly more difficult. Just kind of looking ahead. So we have rate laws, kinetics, and equilibrium. And just as a word of warning, the tutoring center generally does not do a good job on these topics, has been my experience. So don't waste your time there, right? Just ask me for help. I'll be your best resource. So that's my kind of warning, right? Is like, this is the last easy chapter. I've just heard things in the past. Like typically they are unable to solve the problem and then you just waste time at the tutoring center, unfortunately. So yeah, that's my word of warning that it gets a little harder after this. But I mean, we'll get through it just fine. I'm just saying that the tutoring center will not be able to necessarily provide guidance. All right, so then percent by mass. So then we were given mass. We just have to convert it right to the same units. And so we could do, so percent by mass. But if we want to do percent by mass, we need the total mass. And so again, we can figure that out. So that'd be 517.2 grams. And then our ethylene glycol would then be, so 17.2 grams divided by total mass. So again, 15.2. And then calculator. So about 3.33%. I see yeses in class. Excellent. And then chat looks like they also got that. Questions on that one? I don't want to rush it. So then what about mole fraction? What do we have to do for mole fraction? Over total moles. Excellent. So then, so we have moles of solute at least, right? From above. So 0.2771. And then we need to calculate either moles of water and then total moles. So then let's do that. So if we add 500 grams of water, so divided by 18 roughly. So about 27.7 moles. So now I'll add this to get our total moles. And then take this divided by our total. And let's see, just trying to, so chat has an answer, so about 0.98%.
Yep, 0.00987.
Yeah, so 0.00, right? And then move it over, so point,
500.
yes, so 0.987%. Or yeah, like you were saying, mole fraction 0.009877. Excellent. And so that was E. So sorry, I do mole fraction and mole percent. Excellent. Questions on those ones? Pretty straightforward. And so we'll look at this last bit before we take our little break. And so our colligative properties, and so we might do this lab, or at least play with it more. It kind of depends. I'm not sure what we will do for third quarter. I need to figure out some field trip things potentially. But otherwise, another like fun lab to do is to investigate this colligative properties. And so let's look at kind of what this is, and then I'll mention the lab or how you could test this out. And so, okay, like we're seeing, right, the colligative properties just means that these are properties that depend on the number of solute particles, and this also implies with how many, right, they make. And so colligative properties, this is just also referring to like freezing, point depression, or boiling point elevation. So again, all we're saying is we need to take into account the number of particles, right? And we didn't really address this last quarter this well, but now we're really going to make this more clear. And so this means that we have to also take into account into how many particles it disassociates into. And so this is our Van Hoff factor, or called our Van Hoff factor. And so let's just look at kind of the expected Van Hoff and what this means. And so all it's saying is, let's say we have, right, a 1 molar sucrose solution. So that's, of course, a non-electrolyte. And so that means if we have 1 molar of sucrose, it will still be, right, 1 molar of sucrose in solution. And so let's say we take sodium chloride now. So if we take 1 mole of sodium chloride, right? We dissolve it in solution. Well, now it's going to disassociate into two particles. So we're going to make 1 mole of sodium plus 1 mole of chloride ions. So effectively giving us a 2 molar ion solution. So does that kind of track so far? And so the thing to take note, and this is like the real measurement. So it mentions, right, there's some sort of attractiveness and like how well it nucleates, and that actually dictates how much it disassociates. But for our purposes, we're just going to assume however many we expect, right? So for magnesium sulfate, we're going to assume that yes, it does disassociate into two particles, right? We're not going to go by the measured value. That's just kind of showing you how real world doesn't behave perfectly. And then, so looking at magnesium chloride, again, same sort of implication. So we have a 1 molar magnesium chloride solution that disassociates into 1 molar solution of magnesium 2 plus ions, and then write 2 equivalents. So 2 molar of chloride. So then that gives us, right, 3 molar of ions in solution again, effectively. And so again, you can just appreciate this trend. We'll look at iron chloride last. Again, just appreciating how this breaks into 4 effective particles. And so sometimes too, different industries are more interested in like your ions and total ions of things. And so sometimes, like when you keep track of how many things that it disassociates into, this goes into N, or normality. But I'll just kind of leave that there as an aside. So if you ever were to like work in industry, you can look this up. So for example, like Ericsson, Ericsson, the one who like plates all the airplane stuff and helicopters. So they totally work in normalities. And so just for reference. So like I said, different places, different concentrations, and then again, they really care about tracking how many ions everything is disassociating and making. All right, let's take a quick break. So we'll just take our 10-minute break, and then we'll come back to our colligative properties. I mean, it's going to have somewhat to do with just like, it's first the basic, right, solute effects versus solute solvent, right, like how attractive those forces are. So then, yeah, it's just like the electrostatics of that and how well things can solvate. But like you're kind of seeing like larger things are probably more difficult to like surround and solvate, so that's what causes it. And then I forgot to even say like the lab, which is you you compare different like salts for making ice cream and see if one yields better results. Or like rock salt. That's kind of my plan, like maybe for third quarter as like a lab if we need a lab. We do. We obviously need an ice cream lab. All right, I'll let y'all have your break. All right, do we all make it back from break? And then any questions? All right, so let's keep looking at our chapter. And so I think we had kind of implied this last time. So we had kind of mentioned again intermolecular forces, right? And how things either stick to each other or not stick that well. And so now we can look at our vapor pressures. And so a few things. So the vapor pressure of a solvent above a solution is lower than the vapor pressure of a pure solvent. And this is starting to kind of go into the implication of boiling point elevation, right? And what this is implying. So it's basically saying that generally, especially if we're talking about, right, a solid solute, so we'll kind of look at effects from different solvents and the vapor pressure. But if we put in solid, and so now I call this the great pasta water debate, and you know, I'm sure there's like chefs on YouTube that has all sorts of different opinions. But the question is, right, do you salt your pasta water before? And so the idea is, okay, well, if you were to add your salt before, well, that would lower your effective vapor pressure. So you would have to, right, put more energy then into your water to get the water boiling. And so then, right, you can start to make all sorts of arguments about whether that's more or less energetically favorable, or like how that cooks the pasta, whether it's better to have the water higher. So that's the implication that, right, if you put the salt in, then now you're going to have to get the water to a slightly higher temperature. So again, I don't know if anyone is a chef and has any opinions. You want to share any opinions, or I'm just curious. Yeah. That's true. I didn't even think about like the thickening agent of the starch. So yeah, like that's kind of just other things to think about when yeah, when you're bored and the pasta water debate comes up, then you can think about all these properties. But yeah, I'm just kind of putting pasta water. I mean, I like the idea of thinking about the starches, honestly, because that goes into how you make a good sauce. I mean, right? You want to make a good roe for Thanksgiving. Like, got to know how to thicken up your sauces. Anyways, it's always good. All right, cooking is chemistry, too. And, okay, so going back to, again, why this is, right, boiling point elevation, just thinking about what happens. So our solute particles, right, replace some of our solvent molecules at the surface. So that's kind of almost tampering down our solvent molecules. And so then, obviously, right, our pure solvent has an established liquid vapor equilibrium, which we'll look at these graphs. And so if we have, and this is the key, right? So we add a non-volatile solute. So again, implying that it is a solid, generally speaking, and so that will reduce the rate of vaporization. And then our equilibrium will be reestablished, but then, right, we'll have a smaller number of vapor molecules. Hence, again, the implication that you're going to have to raise the temperature, put more energy in to get the vapor pressure right at that same value. And so then we also have this phenomenon where a concentrated solution will draw solvent molecules towards it because of the natural drive for materials to mix. So you can have, right, a solution, and like I said, it'll draw in water from the atmosphere. And again, that will result in a reduction of vapor pressure. And again, the vapor pressure of a solvent in solution is always lower than the vapor pressure of the pure solvent. And again, implying that this is a solid. So this is with a solid solute. And so then we can find the effects by how much that vapor pressure is lowered. And what is convenient is this formula, so we can find the mole fraction of our solute and multiply it by the vapor pressure of our pure solvent, and that gives us, right, our change in our vapor pressure. And so now this is just a little graph of what we saw. So again, our pure solvent versus a concentrated solution. And so if we were to leave this over time, our pure solvent level would drop as it goes into our mixture solution to help mix that. And so like we saw, so this is our formula. And so our we could also solve it the other way, so we could find, right, our moles. So our mole fraction of our solvent, multiply it, right, by our vapor pressure of our pure solvent, and that gives us our pressure in solution. So this is probably the most helpful form of that formula. And then, as this formula implies, right, your mole fraction is always less than 1. So your vapor pressure of your solvent in solution will always be less than the vapor pressure of pure solvent. All right, so let's try that out. So now we're given our scenario here. So we have a vapor pressure at 25 degrees Celsius of a solution contains 99.5 grams of sucrose, 300 milliliters of water, and the vapor pressure of pure water is 23.8 torr. We're given the density. And so what is our new vapor pressure? So how's this coming along? Let's start kind of going through it. So let's see, we need our mole fraction, right? And so I want to figure out my moles of water, or mole fraction of water, right? So we need moles of water over total moles, so sucrose and water. All right, so what do we find for sucrose? So first we have to find the molecular weight of sucrose. So what was our molecular weight for sucrose? You said 342.3? So 0.3 grams per mole, good. And so now 99.5 grams divided by 342.3. So how many moles of sugar do we have? So 0.29. So that's about what I have. You have a question or anything? Just checking. And then, so then 300 mils of water. So 300 divided by roughly 18. So how many moles of water are we given? So 16.7. And so now we can get our mole fraction. And then, right, just kind of sanity check yourself is like, okay, this should be just a little under 1. That makes sense. So 16.7 over 16.7 plus 0.291. Again, that's going to be pretty close to 1, but not. So now I'm just adding. And you guys can tell me what you got for your mole fraction. The mils of water, and then 18, I just kind of roughly gave the molecular weight of water. Yeah, yeah. So I just quickly converted that to 300 grams, right, with the density. So yeah, I was a little quick on that. And then, yeah, so once you converted it to grams, again, keeping in mind density if this was not water, and then dividing. All right, so then do we get about 0.98 for the mole fraction? Good. So then, all right, let's figure out. So times it by the vapor pressure of water. And so that means I get about 23.4 then. So 0.98 for my mole fraction. Sorry, just trying to write down my work now. And so multiplying this, again, by the vapor pressure of our pure solvent gives us about 23.4 torr then for our new vapor pressure. And that's again right just about what we expect. We added a solid in and it's just depressed a little bit. So again, with that boiling point elevation implication that, okay, yeah, I'm going to have to put more energy to get it back to my normal boiling point. All right, let's keep it moving a little. And so, right, this vapor pressure lowering occurs at all temperatures. And so this results in a temperature required to boil the solution being higher than that of the pure solvent. Again, so that's the pasta water argument. And so this also, of course, so right, boiling point elevation. But now we can get into freezing point depression, right? So now kind of what we implied earlier with the wood frog is this disrupts, right, our freezing point. And so now looking at freezing point depression, and so now we're saying, right, the opposite. So again, freezing point depression, boiling point elevation, those are really the two summary points of this chapter. And so now with freezing point depression, so again from our wood frog is implied that the freezing point of a solution is lower than the freezing point of a pure solvent. And this implies, right, why they salt the roads then. We didn't get a lot of ice this year. I mean, that's probably for the better, but right, we still saw how on the few days that it was freezing, people again, we'll salt the road. And so then again, we have our difference of our pressure of our excuse me, freezing point of our solvent minus our solution. So we can find, right, our difference in our freezing temperature. So we have TF, right, for temperature freezing is equal to, and so now, right, other random constants that you have to look up. So it's proportional to this mole concentration with this, so this is molality, which again, I just said we never use molality, and now it's here. And then this KF is our proportionality constant. And this is just, again, a value that we would need to look up, or in the case of your exam, right, I'm going to provide you whatever KF we would need for our problem. And then, again, this is kind of how we'll typically see it, but always, always, always watch your units. So typically, like I mentioned, KF, since it's given in molality, so usually we see degrees Celsius per molality, but just, right, keep your eyes always peeled, because, right, you could always pull a different constant from a different resource with different units. So, but again, we'll typically see this in this class. And so, as you might be aware, pure water freezes at 0 degrees Celsius. At this temperature, ice and liquid are in dynamic equilibrium. And so, of course, right, salt again disrupts that equilibrium. So we mentioned the idea that water makes this nice crystalline structure. And so, again, salt is going to disrupt that crystal pattern formation. And so, right, it doesn't attach to our solid ice, again, creating the disruption. And so now, right, that ice, and so this is another kind of like little caveat on purification. So, right, if you kind of freeze stuff, that's like one way to maybe get out some of the like salty parts. So typically, right, if you freeze something, that'll be more of like a pure ice. So, right, it says when an aqueous solution contains a dissolved solid solute and freezes slowly, the ice that forms does not normally contain much of the solute. So that's all its implication is, right? It's like essentially a purification method. And so obviously this would not be too effective, like trying to get out salt. I mean, you could kind of, right, push salt to the outer rims, but something to think about and where this is used is chemists have this technique called freeze, pump, thaw. And so all that is right, like, so chemists will freeze something, and then once you, well, pump meaning you pump out the head space, and then you thaw back out. And again, right, the idea is that you get out anything that's dissolved, so through this freezing cycle. And so this is how to very effectively get out any dissolved gases in a in solid. So yeah, I mean, so with gases kind of cheap since gases much more easily. But yeah, that's kind of the thought is like if you take it to the limit of 0, yeah, the stuff that's going to be in liquid is going to have concentration of salt. And then the frozen stuff will be more pure like water, if that kind of makes sense. Yeah.
Solute has the lower, or the lower freezing point, so it'll freeze, but the solvent will stay behind because it doesn't freeze. Is that what you're saying?
Well, maybe I like kind of mixed two different things. So I guess like there's two different implications. So like one is like when you freeze something, right, it like kicks out things that are not as part of the structure. So that's what this is saying. So like what Malathi was kind of getting at is like take something to 0, right? What's frozen is typically going to be more like water, and what's not frozen is more like sugar or salt.
Has a lower freezing point, right?
Yeah, yeah. But then like people get a like you can see how like something is not like totally uniformly, right? Like I always kind of see this in like popsicles. Like I don't know if you guys ever have like those fruit popsicles and stuff. And like sometimes they freeze funnily, and like half of it is like a little more melted and like sugary. It's like yeah, it's the sugar first, right? 'Cause it's like not as frozen, and then what's left behind is yeah, like the ice. But then I try to take it to like the next step where it's like if you freeze pump thaw it, that's a really effective way, right? Because the whole point with the freezing of an organic is like, whoop, it's excluded out any gas from its frozen structure, and then pumping it off just exacerbates that process.
I guess my question is just like, is it because of the difference in freezing points, or is it just because like the structure just pushes it out?
It's because the structure pushes it out, right? But that's what causes the difference in freezing points, right? Because like because it has to push it out, like to effectively freeze it, right, you have to bring it to a lower temperature as the implication. So does that kind of help? Yeah. And so kind of somebody was saying the audio was cutting out. But I'm not sure why that would be. Uh, so yeah, implying and like you guys are kind of getting out with these that slow it down and lower the temperature. Yeah, it is also the formation of crystals which do exclude things that don't belong. But again, it's not like a perfect process, right? You can freeze it and then you still have things included. And so now we just have, right, either, so depending on what we're doing, so we have our KF for our freezing constant, so freezing point, and then we'll look at, right, our analogous KB, and then we're always comparing it to our freezing point, and then again, freezing point depression, so we'll figure out the difference based off of this, right, and then that'll lower it, and then we'll do the opposite process, so boiling point elevation, right, you figure out your difference in temperature and add it. And so again, I'll provide you all these things on the exam so you don't have to hunt in your notes for them. And so like we kind of saw, so boiling point elevation, boiling point of a solution is higher than the boiling point of a pure solvent. And again, the caveat being it is a non-volatile solute. So we will take into account how to address a volatile solvent. And then before I get too wrapped up, let's go back and look at these curves. And so just take a second, right? We have our pure solvent in blue here. And this is also a good kind of practice for our states of matter, right? Solid, liquid, gas. So looking again at the orientation, and then we're paying attention to. So right, we have our melting here. Liquid, you can see lower, right? And then looking at this line, liquid to gas, so that's of course our boiling related, showing how that curve has shifted, right? So now it shifts to the right. So again, implying boiling point elevation, that our boiling point, right, has changed for our solution. All right, so let's practice the math. So let's try this and really watch the words on this, and I can scroll up and down. And so what is a freezing point of a 1.7 molality aqueous ethylene glycol solution? Maybe a problem, and then I'll scroll back up. all that. So 1.7 molality solution. So I'll scroll up. Remember, aqueous solution. So aqueous.
I think we're all kind of confused what implication we should take from this.
So what is aqueous mean? Huh? What's yeah, water. So H2O. So yeah, I was trying to be vague on purpose. So yeah, most people get tripped up by this one because they start looking for like the ethylene glycol or something. But yeah, this one was tricky because we have to pay attention to the aqueous. So then what number you're supposed to look at? So we were looking at freezing. So we want to look at this number here for water. Yeah, it was kind of a trick. Yeah, yeah, but it was a little tricky. So yeah, that's what it wanted. And then if you didn't know the normal freezing point, then it was provided on the chart. So I'll try to do that on the exam as well. And so take that 1.86. So see if you can finish the rest of it now. And so once you kind of figure out, right, the tricky wording of this, and it should be straightforward though. Oh, where'd my calculator go? There you are. And so now just multiplying, so 1.7, since it gave you the molality, times the Kf for water, because again, freezing point. And then we get this number, but remember, freezing point depression, so we're saying we lowered this. So, I mean, formally you could do 0 minus the answer. And so that is our new temperature, so negative 3.16 degrees Celsius there. And so other problems you could think about, right? Maybe you want to target a specific temperature and then figure out like how many molality you would need. So that's how these problems would go.
Why is it negative?
Freezing point depression, right? So it's always, the freezing point is always lower.
Okay, so we're adding the negative after the formula to show that it's
Yeah, yeah, and then you always start from the freezing point. So, right, we were at water, so we started at 0 and subtracted. If we had been at these other substances, right, start at the normal freezing point and subtract it. So, yeah, freezing point, depression. So, again, whatever you need to do. So, like star that you're going to be subtracting, and then boiling point elevation. So, you're always going to be adding. Other questions about this one? All right, we'll keep going. So this chapter kind of has a lot in it, but some of it I feel like we've covered. So we're just kind of recovering and re-solidifying. And so you've probably talked about osmosis, maybe in biology. And so osmosis is just defined as the flow of solvent from a solution of low concentration into a solution of high concentration. So generally referring to water. And then there is usually some sort of semi-permeable membrane, biology usually your cell membrane. And then your semi-permeable membrane allows solvent to travel through, but not solute. So then just kind of showing our little example here. So our right side has only pure water, and then our left has solute. Then we can see how the water level rises. And so this rise then is referred to our osmotic pressure. And so this is defined as the amount of pressure needed to keep osmotic flow from taking place. And then, so osmotic pressure is just defined as this capital pi, and it's proportional to our molarity. So then it's molarity times R times T. But then don't forget our Van Hoff factor, right? So how many particles it dissociated into. And so that's, we'll probably look at the homework on Thursday together. But that's part of the trick of the homework is like, for the comparison part, you have to figure out, well, how many particles does everything dissociate into before you start comparing. And then, so looking at this, right, this is relevant again in biology and medicine. And also, right, like why your saline is a certain percentage of, right, 0.9% of salt, I believe it is. And so we have these terms. So we will need to know these vocabulary terms. And so biology uses this isoosmotic solution, but chemists usually use the term isotonic. And so isotonic means that the solution has the same osmotic pressure as the solution inside the cell. So just like implying your normal red blood cells, right? Normal homeostasis. And then, so let's surmise what could come up with, how would you get this scenario of shriveled blood cells, right? And so this is where you have a hypertonic solution, where your solution has a higher osmotic pressure than the solution inside the cell. So water flows out of the cell, right? Trying to compensate for that. So what could be an example? Or maybe not even so extreme, but what can you think of? Yeah, drinking salt water, lots of fatty, greasy foods, or right, like salty foods, salt water, right? I mean, you could get into why salt water isn't hydrating because of that effect. And so now looking at our other scenarios, so hypoosmotic solution, or hypotonic would be the chemist's term. So this is when a solution has a lower osmotic pressure than the solution inside the cell. And so that means there's a net flow of water into the cell, which could cause it to swell. And so what's kind of the example, the real life example of this? Probably talked about it in your biology classes. You ever hear the danger of like those gallon challenges? Yeah, all those things. It's exactly it. So yeah, I always say, right, the gallon chugging, anything that involves chugging large amounts of solvent. So gallon challenge. So yeah, right, the danger in chugging large amounts of water is then, right, this happens where obviously, right, your solution becomes deprived. And so then it tries to flow into the cell. And then, like you were implying, right, if it implies to the cell so much that the cell bursts, well, then you can have consequences like death and blindness and all sorts of horrible things could happen, right? Like people have died from doing these radio contest gallon challenge things, trying to win tickets and stuff. So, yeah, that's why real danger. Questions on that? Okay. See how far we'll get. Maybe we can get through the math of this. So now we're going to figure out, well, how do we deal with another volatile solute? And so now let's look at what this is saying. So when we have both our solvent and our solute, right, so basically they're both liquids, so both can evaporate, then that means that we have molecules in the vapor phase. And so now in an ideal solution, the solute-solvent interactions are equal to the sum of our solute-solute and our solvent-solvent interactions. And so all that is saying is for, again, an idealized solution that we would expect our pressure to just be, right, our pressure of our solute plus our pressure of our solvent, right? And so that's basically just gas laws, right? Everything is additive. And so, right, we see that a solvent decreases the solute vapor pressure in the same way the solute decreases the solvents. So, right, just looking at our molarity or mole fraction calculation. And so, just again, appreciating this graph for a second. So again, just saying that they're additive, right? So we can add these two components, and then this gives us our total vapor pressure. However, right, so we can have two different cases. And so if our solute-solvent interactions are stronger or weaker, then it's non-ideal, right? So we have two different scenarios. So let's say we have when our solute-solvent interactions are stronger, right, than our solute-solute plus solvent, then our total vapor pressure of the solution will be less than predicted, right? So kind of think about for a second what's that implying. So it's basically implying that the solute and the solvent just happen to be, right, more attracted to each other than they are, right, with itself. So that's all that's implying, right? So if it's more attracted to the other solvent, then we can see how that's going to, right, lower our effective vapor pressure. And again, right, all we're saying is it's a lower than what we would expect. So this is, again, just showing this. So we have strong solute-solvent interactions. And so again, that's going to lower our additive vapor pressure. And then, right, we could also have the opposite. And I feel like this usually tends to be more the case when our solute-solvent interactions are weaker than our solute-solute, our solvent-solvent, then our total vapor pressure will be more than predicted by, again, our additive assumption. So yeah, this is the one that would be relevant, right, with the mole fraction. So you need to find the mole fraction of each and then add them, which we'll do in a second. And so now let's try that. So I think, like I said, I think we'll have time to finish this, or at least we'll start looking at it. So let's go through this. So a solution has 3.95 grams of carbon disulfide, CS2, which is somewhat toxic, by the way. So do you know what CS2 is analogous to? What's in the same?
CO2?
Yep. Right. So now you can understand, right, why it's toxic. Also, those sulfur bonds tend to bind just a little bit stronger to the iron hemes. Anyways, so we have 3.95 grams of carbon disulfide, 2.43 grams of acetone, and the vapor pressure at 35 degrees Celsius of the pure carbon disulfide and acetone are 515 and 332. And so then, assuming ideal behavior, calculate the vapor pressures of each component. And then it tells us our experimentally measured one. And so we want to compare then our bond strengths. So go ahead and at least start that. So see if you can figure out, right, what is our true, or excuse me, what is our ideal vapor pressure, right, assuming ideal behavior. So find our mole fraction. Then we'll go from there. So let's start going through this. So, right, we need to find moles of everything. So that would be kind of my first step. So let's find moles of carbon disulfide. So 3.95 grams divided by, what do we get for the molecular weight of CS2? So grams per mole, excellent. And then comparing that to acetone. So moles of acetone. So 2.43, and then what's the molecular weight of acetone? 46. I have it. Yeah, I have 58.08 roughly. So that, yeah, just double check all those. And so then for moles of CS2, what do we get?
Got 0.0519.
So 0.0519 moles. Good. And then so acetone moles, 0.0418 moles. So this is looking good. And so now we have to calculate the mole fraction separately, right? So going back to our formula here. So we want to figure out our new pressure based off of the mole fraction, right, times our pure solvent. And so we have to do that again for each one. So for carbon disulfide, let's find our mole fraction. So over total moles. And then once we find that, right, multiply it by its pure vapor pressure, so 515. And then repeat the same for acetone. So 0.0418. Again, multiply it by pure acetone, 332. Now, sorry, just trying to write this out. So 0.553 roughly times 515. And then, right, adding it with our second component, so 0.447 times 332. Oh. And so then what do we get for our total? And then again, this is our ideal, right, vapor pressure. So what do we get for our ideal vapor pressure? Oh, 6, I got. Oh, sorry. So you were comparing it? Yeah, so we're comparing it, sorry, so to 645, correct. And then, so do we get 433 for the ideal? And then, right, we're comparing it to 645. So then what's the implication? What can we tell from, right, what our idealized vapor pressure should be compared to what it actually is? What does that tell us about those interactions of the acetone or carbon disulfide to acetone interactions?
It's lower than the ideal, which means the solute-solvent interactions are stronger.
Right, other way, because the ideal is lower, right? Because we found that it was higher. So then the interactions are weaker, right? Does that make sense?
Isn't the 645 the ideal one, and ours is the
No, other way, because it says the experimentally is determined. Yeah, so it's experimentally determined to be 645 torr. So then it's higher. So again, experiment. And since it's higher than the ideal, so this implies that, right, our CS2 acetone interactions are extremely weak, right? So then that's what creates the more volatile interaction there. And so then you could think about, well, is that true, right? Are they weak? And I know we're kind of out of time, but we could look at this really quickly. And so comparing the structures, so acetone looks like so, and then CS2. So what's the difference between these two? What can we say about this molecule versus this one, thinking in terms of polarity or non-polar? Yep, so acetone, polar. This one is more non-polar. And so now this is further explaining why those acetone and CS2 interactions are relatively weak, right? So going back to like dissolves like, well, these are more unlike, so they actually have kind of weak interactions there. All right, pretty good. We'll stop there for today. And then I would still really appreciate any sort of positive reviews and stuff. Yeah, that would really help me out. All right, I'm gonna end stream for today. Email me, of course, if there are any questions, and then we'll have lab today. So it should be a really fun lab, like I said, with the titration. But we'll look at the math on the titration on Thursday. All right, I'm gonna stop the stream, and then I'll see